Hi, my name is Zain Khan, and today I'll be talking about my research evaluating generalization and transferability in foundation models for ocular diseases. So why does the automated detection of retinal disease matter? Well, there are more than 2 billion people that suffer from a preventable vision impairment globally. Out of these, 191 million people are estimated to be affected by diabetic retinopathy by 2030, DR being only one type of ocular disease. And currently the average wait time for a diagnosis from a specialist in the UK can take up to 6 weeks, which is very long. So there is a clear gap. That gap is the shortage of ophthalmologists, manual diagnosis being slow and subjective to factors such as bias and reliance on specific clinical setup, and if and when AI models are used, they require labeled data, which is costly to obtain because medical data is scarce to begin with. Hence there is an opportunity, and the opportunity is to use intelligent AI models such as foundation models, which have been pre-trained on unlabeled data with fine-tuning to overcome the problem of data scarcity. So the question becomes, how well do they generalize to different modalities of data and transfer to unseen tasks? So the central research questions that this dissertation investigated was, how well do state-of-the-art retinal foundation models and general foundation models, where the retinal models are RETFound and UrFound and the general FM is CLIP, how well do they generalize and transfer across diverse ocular disease tasks in a scenario where data is scarce? The second question is, do adaptation strategies help FMs adapt better to downstream tasks compared to their pre-trained knowledge? FMs were applied to 3 different tasks: DR grading, glaucoma classification, and multi-disease classification for ocular and systemic diseases. The approach is shown over here, where for each of the 3 tasks, their data sets were collated and were essentially taken from the web. Leave one out data set was also used, the LoRa strategy, for ablation. Notice that for multi-disease classification, only one dataset was used, but this dataset included 10,000 samples, and this was specifically due to time constraints. Pre-processing is then done, which includes image augmentation, and then the models, for each of the models for each task, adaptation is then done, either through LoRa or through linear probing. ResNet 50 is included here to serve as a baseline model to be compared against the FMs. Also notice that again for multi-disease classification, due to time, only 2 of the models could be compared against one another, and that is RETFound and ResNet 50, meaning only 2 could be applied for this task. Loss is then applied as the next stage, and then evaluation. The implementation details are shown over here. However, due to time, we won't go through all of this. However, we can notice that for the hardware, the RTX A4000 GPU was used with 16 GB VRAM. So notice that only one GPU was used to fine-tune all of these models and evaluate them. The evaluation metrics are also shown over here. So there are clinical performance metrics, the standard metrics, as well as the visualized metrics, so the confusion matrices and attention maps. We have statistical tests to measure disagreement, overlapping probability distributions, and then we have computational benchmarks. These metrics have all been included for clarity, as well as being mindful of clinical relevance. The results are shown over here. So for DR grading, firstly, CLIP with LoRa achieved the best performance and actually outperformed domain-specific models. For glaucoma detection, UrFound LoRa, due to its domain knowledge, demonstrated the best glaucoma detection by identifying subtle changes in the optic disc, whilst CLIP LoRa followed closely behind, and this showed that strong transferability across both the retinal-specific and general vision models existed for this task. For multi-disease classification, RETFound LoRa achieved a stronger performance over ResNet 50, specifically for the well-represented disease classes. However, it still struggled on the minority classes, which seemed to be a very big problem or limitation in this research. Overall, the conclusions are that adaptation is equally as important as domain pre-training. Domain pre-training is useful for subtle features, and data poverty is the biggest constraint. I hope that's provided clarity into my research. Thank you for listening.